but the Bronsted-Lowry definition is very useful, and we will start with that. According to this definition, acids are proton donors and bases are proton acceptors. Since a proton is located inside of the nucleus of an atom and therefore can never leave the atom, we consider hydrogen ions protons because the hydrogen had one proton and one electron. Once it lost that one negatively charged electron, it now has an overall positive charge due to the one remaining proton. It also has a neutron, but that has no charge. So it'll then be our job when we see a chemical reaction to identify an acid based on its behavior. What is it doing? And so let's practice reading this chemical reaction together and see which substance is donating a proton and which is accepting. So the first one I see here, HA, starts out with a hydrogen ion, and then on the right side after the reaction, only A remains. It has lost that hydrogen ion. So from beginning to end, I can identify this as an acid because it has done what acids do. It has donated a hydrogen ion. It has one less, and it has a negative charge as a result of losing that positive thing. Alternatively, I can see that water here started out with two hydrogens, and now on the other side of the reaction, it has three. So it is a base because it has behaved as a base. It has accepted a hydrogen ion. Now, I know you may be thinking water isn't a base, it's neutral. That is somewhat true, but actually water can behave as either an acid or a base. The term for that is amphoteric. And so we may come back to that later. Here, we want to identify conjugates. To conjugate a verb is to find an alternate form of that verb. Asks us to identify the conjugate base for the following acids. It's telling us these are acids. So if this is an acid, it should do what an acid does. That means donate a proton. So when this first substance donates a proton, it will become ClO4 with a -1 charge, right? Because it got rid of something positive. This next one, when it donates a proton, it will become NH3 with a neutral charge. It had a positive charge, now its charge is neutral. And likewise, H2 with a -1 charge. And what about this last one? Perfect. What about these? Identify the conjugate acid for the following bases. So we'll be doing the opposite this time. Bases are proton acceptors. So if this first substance accepts a proton, we will write it like this. Notice it has a neutral charge now, and likewise. Now you might be wondering, why didn't I clump all of the H's together? Sometimes we write it on the front, it's very often, because we want the reader to recognize that H as an outstanding component of this molecule. It is something that may come off, and that's what makes this look like an acid to the reader. If I bury it in the middle, it doesn't look like it may dissociate from the molecule, and that's the definition of an acid. It's a proton donor. So if it's something that gives up its proton, it's helpful if that proton is written in the front. All right, so that's one skill we want to practice. Remember, only strong electrolytes break apart, that is, soluble salts, the 7 strong acids, and strong bases. So in this next section, we're going to practice writing those 3 types of equations. And when we do, the things that will ionize or separate or break apart in that complete ionic equation will only be the strong electrolytes, the soluble salts, the 7 strong acids, and strong bases. Remember, only substances that are both aqueous and strong are broken apart into ions. If it's a weak electrolyte, or water, it should be written intact. You will need to know and memorize the 7 strong acids. So the 7 strong acids, I have a little acronym to help us remember these, and it is I, so, bro, clo, and the class's response will be no clo clo. So when I see you in the hallway after today, I will raise my hand to you and say, isobroclo, and your response should be no clo clo. That's how we'll remember the 7 strong acids. Now, obviously, they all have hydrogens written in front because we expect them to be hydrogen ion donors. And the hydrogens for acids are often written in front to indicate that to the reader. Um, the second one has 2 hydrogens written in the front because SO4 has a 2 minus charge, but the rest of these are just neutral molecules. If the ion in the back has a -1 charge, then there's only 1 hydrogen bound to it. So they're all written in a neutral format. So only these 7 acids will dissociate or ionize, in solution as. Now, should both of these be aqueous, let's go back and decide. Only strong electrolytes break apart. That's soluble salts and the 7 strong acids. So H2S has an H written in front to let us know it's an acid. So if this is an acid, is it one of the 7 strong? It is not. So they're aqueous, but intact. It is aqueous, but it is not strong, and only substances that are both aqueous and strong are broken apart. I'm not writing it as a solid because it is not a salt. It is not a metal, non-metal, ionic compound. I am writing it as aqueous, but in the next step, I will not separate it. Moving on, Na3PO4. It is a salt, and according to the rules, would this be a soluble salt? Let's take a look. Rule number 1, nitrate salts are soluble. This does not have nitrate. Rule number 2, the, the metals in the +1 column along with ammonium are soluble. This one fits in that category, so I'm going to write this one as an aqueous salt. Let's move down and write the complete ionic equation. So the first 2 reactants have been written as dissociated in the solution. I wrote the ions out. And then the products, remember I'll keep H2S together because in order to separate it, it would have to be both aqueous and strong. This is only aqueous, it is not strong. And then I'll separate, not balance these, so let me go back and do. Okay, and finally, I'll write the net ionic equation. Here we have a spectator, so I'll go ahead and take that one out on both sides. Do you see any others? PO4 appears to be a spectator. It doesn't change from the beginning of the reaction to the end. And everything else looks like it takes part in the reaction, so I'll go ahead and write these closely together, and that's my net ionic equation. Let's practice that a few more times. So here I have HNO3 on the left and LiOH on the right. Let's start with the double replacement reaction. I'll have, aha, a strong acid and a strong base make water, so many of these chemical reactions will produce water. HNO3 is a member of isobroclo, no clo-clo, and lithium hydroxide is a strong base, which you'll see from tonight's homework. So it's very common that together these will make water. Water is always written as a liquid. It's never written as broken apart. It doesn't ionize. It is very neutral. I am aware that as a reactant, it can be forced to behave like an acid or a base, but as a product, it's simply water and salt. So what's the salt that's being produced here? Lithium nitrate. I'm going to put an aqueous symbol there, and I think you know why. Because rule number 1 states nitrate salts are soluble. So since this has nitrate in it, we know it's going to break apart and water will not. Now, if I was to go ahead and write the complete ionic equation, which ones of these would I separate? I would certainly separate the reactants, right? Because we cannot write these reactions at all if we don't assume that we've been given two solutions. Then what would I separate on the product side? We never separate water. It is always written intact as a product. It is always written as a liquid. If it was on the reactant side, we could separate it because we're being told it's some solution. But that won't happen for the most part. Now, will I separate lithium nitrate? Yes, I will, because it is a soluble salt, rule number 1, and it's aqueous. So if I wrote this as a complete ionic equation, I would separate everything except the water. So therefore, in my net ionic equation, I would have the water on the right side and what on the left side? Just the two things that go into making the water. So I can quickly do that because I'll have hydrogen on the left side, hydroxide on the left side, and water on the right side written as a liquid. This would be my net ionic equation for this reaction. And it often will for a strong acid, strong base. They basically make water. One donates a proton, one accepts a proton, and together they produce water. So actually, as you get good at these and start recognizing strong acid, strong base combinations, you'll know to jump straight to that outcome. We'll do one more together because the rest of these have at least one weak substance. Here we have a weak acid. I know it is an acid because it starts with a hydrogen. We write the hydrogen first in acids so that the reader identifies it as an acid. This is a strong base. I know that because a metal and a hydroxide group are a strong base. Metal, hydroxide, metal, hydroxide. What about the next one? Is this an acid or a base? It's an acid because it starts with a hydrogen. Is it a member of isoprocyl? It is. So therefore, it's one of the 7 strong acids. How about over here? Is this a strong base? It's not a strong base because it's not a metal hydroxide, it's ammonium hydroxide, which makes it a weak base. Let's look at the next one. Is this an acid or a base? I know it's an acid because it has a hydrogen written in the front. Is it one of the 7 strong? Is it isoprocyl? It is not. So therefore, it is a weak acid. It'll be written intact. And how about this one? Notice a metal hydroxide here. We have a strong base. So at this point, you may be wondering if I can recognize acids because they always begin with a hydrogen, and I know the strong acids because I've memorized isoprocyl. And how can I recognize bases? Well, in tonight's homework, you're going to find out that there's 2 types of bases, weak and strong. A metal from either the +1 or +2 groups on the periodic chart and a hydroxide. That constitutes a strong base. Metals that are transition metals with a hydroxide are not strong bases. You'll also find out that weak bases have derivatives of ammonia. Any form of NH4, NH3, NH2 that makes a weak base. So by doing tonight's homework, you'll be able to identify strong acids and strong bases. But let's go ahead and choose this last one and we will complete it together. We'll do a double replacement reaction. Cn is one of the polyatomic ions on the back of the periodic chart. Cyanide, it has a -1 charge. So when I write it with sodium, I'll just write it in a 1-to-1 ratio. And then I'll have to check the rules to know if it is soluble or not. Rule number 1 for salts, nitrate salts are soluble. Rule number 2, the +1 metals, this contains a +1 metal, so therefore it must be soluble. Okay, so now when I write the complete ionic equation, I will only separate the substances that are both strong and aqueous. So let's look at the first one. Is this a strong acid? No, so I write it intact. The second substance, is this a strong base? Yes, so I separate it. The third one, water, I always write it intact. The fourth one, this is neither an acid nor a base, it is a salt, so I consult the rules. According to rule number 2, I should break this apart. I'll go back and make sure that these are all balanced. They do appear to be balanced. And now I can write the net ionic equation. So I'm going to go ahead and copy this and see what this looks like. This is a unique, so when you have either a weak acid or a weak base, you're going to have some residual hydrogen or hydroxide left in the reaction. Here, since it was a strong base, there's some residual hydroxide left, and the acid is intact, so that looks reasonable for that one. So go ahead and try